Just looking on for what we have working with polynomial functions, and last time we looked into zeros and their multiplicities, and for what we have from section 2.2, okay, we have for a given polynomial function f of x, okay, here we have a third order expression where we have four terms, and now we have the expanded form layout for this particular polynomial function, and we're going to go from the expanded form to the factored form, whereupon we will be able to identify the zeros from the individual factors, and utilizing the degree of each factor we will be able to identify the multiplicity of each of the zeros. Okay, now for what we have in this problem, okay, now this is not going to be the orthodox type of factoring by grouping, because here we looked at working with second order trinomial expressions where we had split up like a first order term into two distinct terms in the same variable and the same degree. And for what we have for this four-term expression, okay, I can still factor by grouping, again separating the first two terms apart from the last two. And the reason for this is that I do have the coefficients and degrees aligned so that I can factor by grouping. Okay, notice we have the coefficients have like a 2-to-1 ratio, and with the last two terms they have like a -50 to -25 ratio, and that is also a 2-to-1 layout. Okay, and if we look at factoring by grouping, okay, so I'm going to cluster together the first two terms in parentheses. Okay, so combining x cubed and 2x squared, and notice we have the last two terms. Okay, we have the operation that separates the first two terms from the last two terms. Okay, that is going to be subtraction, and if I quantify that which represents -25 minus 50, or minus 25x minus 50, factoring out the -1 to represent the subtraction portion, and we have say we have for -25x, again you have the negative of 25x, and for minus 50, think of envisioning upon factoring out -1, we have times 50. And you can always go back and make sure that you have the right quantifying of the parentheses. Okay, so you have x cubed plus 2x squared, and removing the second and last group of parentheses, okay, you have what's going to be minus over 25x, and minus over 50 becomes -50. Now, in looking at drawing out the greatest common factor from each of the pairs, okay, so we have an x cubed and 2x squared. Okay, we have both terms are in the variable x, and the greatest common factor is going to be the lowest, or I should say the lower degree appearance of x, and in this case we'll have x squared, and here we have x squared into x cubed plus 2x squared, so this will go x plus 2 times. And upon subtracting now between 25x and 50, okay, we're going to place the greatest common factor after the subtraction sign. Okay, so between 25x and 50, greatest common factor is going to be 25. And we will have 25 into 25x plus 50 to also go x plus 2 times. And for what we have in the follow through, okay, notice we have in both groups the common binomial x plus 2, and clustering together the outside terms in operation. Okay, so you have x squared minus 25 and so we have x plus 2, and for x squared minus 25, okay, we have a difference of squares, so I can factor even further. So we have x squared minus 25. Okay, so this will go to x plus 5. Times the quantity of x minus 5. So this is going to be the factored form. And looking at what we have in identifying the zeros and their multiplicities. Okay, so you got, again, for the factors, you have x plus 2 and x plus 5. And x minus 5. Okay. All right. And you do not see a raised power outside the parentheses for any of these binomial expressions, but we do have implicitly that x plus 2, x plus 5, and x minus 5 will be a first order. All right. And looking at the zeros of this polynomial, so first of all, okay, for x plus 2, okay, if I set x plus 2 equal to 0, okay, we're going to have that x is equal to negative 2. And again, since we have x plus 2 to implicitly be of first order, okay, we're going to have negative 2 is going to have a multiplicity of 1. And we have for x plus 5, okay, if I set this equal to 0, we have x equal to negative 5. And since we have the factor x plus 5 of first degree, okay, we have the multiplicity also at 1. And with x minus 5 equal to 0, we have x equal to 5. And since x minus 5 is first degree, okay, again, we have this third 0 to also consist of the multiplicity value of 1. Okay. Now, for what we have in the case of the next item, for number 28, okay, now we have, this time we have representing y. Okay, we have in functional notation, we have n of x, and we have also provided in expanded form. Okay, we have x to the 6th plus 4x to the 5th plus 4x to the 4th. And just like number 23, okay, we can factor and this time around, okay, we can start out by taking the greatest common factor. So we have all of these expressions are variable terms in the letter x, and the greatest common factor is going to be x to the 4th. And so for the initial factoring, okay, so we have x to the 4th, and into this trinomial, okay, this will go x squared plus 4x plus 4 times. And we can factor this trinomial. So the process of factoring continues. So you have x to the 4th, and for x squared plus 4x plus 4. Okay, so we have with x squared, okay, this will go to x and x. And factors of 4 that will add up to 4. We will have it 2 and 2. And we have x plus 2, okay, is a repeating linear factor, and condensing in terms of a raised power. Again, we have x to the 4th, and for x plus 2, since this appears twice, we can make the notation compact, whereupon we have x plus 2 raised to the degree that matches the number of times it appears when expressed along the lines of multiplication. Okay, so in this case, we're going to have x plus 2 squared. Okay, so we have n of x, okay, is equal to x to the 4th and once again we have times the square of x plus 2 And for the zeros, okay, we have the variable factors at x as well as x plus 2. And from x, okay, we have 0. And we're going to have the multiplicity value to be the degree to which x is raised, and so that is going to be at 4. And for x plus 2, okay, we're going to have x is equal to negative 2. And since we had x plus 2 to repeat, whereupon we had it expressed as the square of x plus 2, okay, it's going to turn out that negative 2 is going to have the multiplicity of 2. Okay. Now, for what we have in the next item, now we have, this time instead of expanded form, we had the polynomial to be expressed in factored form. And here we have that y is represented by p of x. And so we have is equal to negative 3 times x. We have times quantity of x plus 2. We have raised to the third power. And we have times the quantity of x plus 4. And expressing what we have, let's say just stressing the degrees. Okay, so you've got 3 variable factors with x, x plus 2, as well as x plus 4. So you got negative 3x. Okay, so you have a first order variable. And we have times quantity of x plus 2, which we have to the third. And we have for the quantity of x plus 4, okay, there's no explicit power, okay, to which this is raised. Okay, so just x plus 4 alone, okay, we have that this is implicitly to the first degree. Okay, so we have the factored form already laid out. And for what we have in the case of the zeros, okay, so for the first variable factor, that is x, and the negative 3 alongside it, okay, that's just a numerical coefficient, just like a multiple of x, and or a constant, which is just going to be a multiple of x. Okay, so the variable factor we have x, and so we have 0, and since that x is to the first order, we have that the multiplicity is equal to 1. And for x plus 2, okay, we have negative 2. And for that, we have the multiplicity is equal to 3. And from x plus 4, okay, so we have negative 4. And since that factor is a first degree, okay, negative 4 is going to have a multiplicity of 1. Now, for what we have in the case of number 30, okay, like number 29, okay, we have this polynomial presented in factored form, and we have q of x, whereupon this is set equal to negative 2 times x to the fourth, and we have times the quantity of x plus 1 raised to the third, okay, and then we have the quantity of x minus 2 raised to the second, okay. And so I'm just going to rewrite this, okay, so just stressing the degrees, okay. So again, we have negative 2x to the fourth. We have times the quantity of x plus 1 cubed times the quantity of x minus 2 squared Now for what we have in the case of the zeros, okay, again, just like negative 3 from number 29, we have with negative 2, this is just a constant multiple, and so the variable factor at the front is still going to be x, and we still have that the 0 value is 0 itself. Okay, so we have 0 from x, and since x is raised to the 4th power, okay, we have 0 is going to have a multiplicity of 4. And from x plus 1, okay, the corresponding 0 is going to end up at negative 1. And since we have the cube of x plus 1, negative 1 is going to have a multiplicity value of 3. And for x minus 2, okay, the 0 of this is going to be at 2. And since the factor is squared, well, 2 is going to have a multiplicity value of 2. All right, and so far we have had integer values throughout for the zeros, okay, and that is not necessarily always going to be the case. And 38 is going to provide such a counterexample. And for number 38, okay, this time we have the function m of x is equal to the difference between x to the 5th and 5x cubed. So we have a difference of variable terms in the same letter. And here, okay, the greatest common factor is going to be x to the 3rd. And upon factoring out x cubed, so we're going to have x cubed as one factor, and then we have x squared minus 5. And in terms of drawing out the zeros, okay, now 5 is not a perfect square value in the integers, but we're going to treat the difference binomial as what we have with the difference of squares. So for difference of squares, okay, have x squared minus p, and for the breakdown this would be x plus and x minus the square root of p. And so for what we have in following through, we'll have that m of x is equal to x cubed. Okay. And again, we have with x squared, okay, we have factoring out to x and x. And again, we have with p represented by 5, again, we have plus as well as minus the square root of 5. So this is going to be the factored form, and just setting things up, again, emphasizing the degrees. Okay, so we have with x, okay, that's going to be to the 3rd. And we have x plus the square root of 5. Again, no explicit power, so we say that it is raised to the 1st. And likewise, we have x minus the square root of 5, also raised to the 1st. So we have in the case of the zeros and their multiplicities. And once again, we have with just the x factor, okay, we have 0, and we had that the multiplicity is equal to 3. And for x plus the square root of 5, if I envision setting this equal to 0, well, taking away the constant on both sides, okay, so you would have that x is equal to the negative of the square root of 5. Again, this will have a multiplicity value of 1. And for x minus the square root of 5, so if you envision setting this expression to 0 and adding the constant to both sides, okay, we'll have that x is equal to the square root of 5. And the square root of 5, okay, is also going to have a multiplicity of 1. Okay. And now the values of multiplicities, okay, they will play a significant role in terms of how the behavior of the graph of the function is going to align with what we have concerning the x-axis. Okay, and we'll get into that shortly. And I'll tell you what, just for the next few moments. Let's say if we're looking for the zeros and multiplicities. Okay, for the following functions, okay, just a couple of items here. And we'll say we have, for the first, let's say we have f of x is equal to 2x to the 4th plus 4x cubed plus 2x squared. And we'll say that we have for the other, we'll say that we have f of x is equal to x to the 6th plus 10 times x to the 5th plus 25 x to the 4th. Okay. Okay, if we go ahead and look into these, we have, again, determining the zeros and their multiplicities. We have with the first function, okay, so we have a fourth order trinomial expression whereupon we have 2x to the 4th plus 4x cubed plus 2x squared is going to be that which defines what we have for y is equal to f of x. And looking at transitioning from this expanded form to its factored form, and we have with these three terms, okay, we have even valued numerical coefficients throughout, and we have all these terms are variable expressions in x. And it's going to turn out that the last term in the trio is going to be the greatest common factor. So if we factor 2x squared, then we'll have, in the process of expressing in factored form, okay, so you got 2x squared into the trinomial. So this is going to be x squared plus 2x plus 1. And with 2x squared factored out, okay, we have the trinomial that remains can be factored still. And so we have with x squared plus 2x plus 1, okay, we're going to have an identical factor with x plus 1. So again, we have x squared plus 2x plus 1 is another one of those squared trinomials. And we had established quite a few of them when we looked at the completion of the square. So we have in factored form, okay, so you got 2x squared. And for compacting what we have with the repetition of the appearance of x plus 1, okay, we'll have x plus 1 raised to the second. And looking at the zeros and their multiplicities, okay, so we have f of x is equal to 2x squared. And we have times the quantity of x plus 1, which will also be squared. And so for the zeros and their multiplicities, So again, we have the x factor. Okay, so we have 0. And since we have x to be squared, okay, so 0 is going to be a multiplicity value 2. And for x plus 1, okay, the corresponding 0, we have at -1. And since x plus 1 is squared just like x, -1 also has a multiplicity value of 2. Now, for the second function, okay, we have, just like the first one, we have expressions in x throughout. And okay, now the greatest common factor, okay, is going to be limited to the lowest degree appearance of x. And so we're going to have an x to the 4th. And factoring, okay, so x to the 4th will go into this original trinomial, x squared plus 10x plus 25 times. And factoring once again, okay, so just like x squared plus 2x plus 1, x squared plus 10x plus 25 is another square trinomial. So the factoring leads to the repetition of x plus 5. And so writing in factored and condensed form, okay, so we're going to have the f of x is equal to x to the 4th times the square of x plus 5. And again, just emphasizing or highlighting the degrees. Okay, so I have x is raised to the 4th, x plus 5 is squared, and again the degrees will signal what the multiplicities of the corresponding zeros will be. Okay, so again we have the reappearance of x, so we have that 0, and the multiplicity value is at 4. And with x plus 5, okay, we have -5. And since the factor is squared, -5 is going to have a multiplicity value of 2. All right. Now, for what we have in the case of the significance that multiplicities can play in working with what we have in graphing. And we have regarding multiplicities. And there are two distinct modes of behavior that f of x will adopt, okay, whenever it is being graphed, okay, if we have both cases to arrive. Okay, so first of all, we have in graphing, okay, f of x, okay, will cross the x-axis. At zeros of odd multiplicity. Okay, so it crosses, okay, whenever you have the multiplicities, okay, to be odd values. Okay, now for the even values, okay, f of x, okay, without crossing the x-axis, it is going to touch the x-axis. So in graphing, okay, so we have f of x touches the x-axis. at zeros of even multiplicity. And just looking at how that particular set of dynamics will play out. And let's say that if you have we have for a function f of x, and just displaying in factored form. So we can say we have f of x is equal to x plus 2 to the fourth. And say we have times x minus 3 to the second. Then we have times x minus 6 also to the second. And say we have times the quantity of x minus 10 to the third. And in looking at the zeros and their corresponding multiplicities, okay, again, just highlighting the degrees. Okay, so you have with the zeros, okay, and I'm going to stress the variable expression in these and kind of do a little bit of display, a little bit of a different display for the zeros and their multiplicities. Okay, first of all, okay, we have with x plus 2, if that is equal to 0, we have x is equal to negative 2. If x minus 3 is equal to 0, we have that x is equal to 3. For x minus 6 equal to 0, okay, we have x is equal to 6. And for x minus 10 equal to 0, okay, we have that x is equal to 10. Okay, and we have for the multiplicities, okay, so we have negative 2 from the fourth order factor, that will be a multiplicity 4. 3 stems from the square of x minus 3, so the multiplicity value is at 2. 6 stems from x minus 6, which is also squared, so that multiplicity is also at 2. And for x equal to 10, this comes from the cube of x minus 10, so that multiplicity is at 3. And in terms of what we have for those zeros, in terms of whether you're going to have the graph to cross or touch the x-axis, and just for the rule of thumb, okay, so in graphing, f of x will cross whenever the multiplicity is odd, but it's going to touch whenever the multiplicity of that zero is an even value. Okay, so if you notice, we got for the multiplicity, you got 4, 2, and 2. All these are even values, and it is only the last multiplicity value of 3 that we end up with an odd amount. Okay, so with even multiplicities, okay, so in terms of crossing or touching the x-axis with an even multiplicity, okay, this is going to touch the x-axis. And in terms of the location, it's going to touch at that 0. So it's going to touch at x is equal to negative 2. And the next even multiplicity, okay, have signaling that at that 0, okay, the graph is also going to touch the x-axis. It's going to touch at that 0, which we have with x is equal to 3. And next multiplicity value is even, and it's going to touch at x is equal to 6. And then we have with the last multiplicity value being an odd amount. So this time it is going to cross the x-axis. And it's going to be at that corresponding 0. So it's going to cross at x is equal to 10. And so for the pattern that is going to arise. Again, we have with the XY coordinate system. Again, I'm not going to draw this according to scale, but just key locations. Okay, so you have x at -2. And we have x at 3. And we have x at 6. And also we have x at 10. Okay, so we have with these zeros. Okay, so these zeros are going to be x-intercepts. Again, for what we have here, so we have at -2 it touches, x equal to 3 it touches, x equal to 6 it also touches. And once we get to x is equal to 10, okay, it is then that the graph of the function is going to cross. Okay, so we have for the graph itself, okay, so we have for f of x. Okay, now the graph is going to start underneath the x-axis. Okay, and it's going to rise, and once we get to the x-axis, once we get to x is equal to -2, again it's going to touch but not cross. So it's going to essentially like bounce off the x-axis and it kind of go through a round of going up again. And once we get to x is equal to 3, you have another touch but not crossing, and you have it's going to descend and then rise up again. And once we get to x is equal to 6, it touches once more. And then once we get to the next and last of the x-intercepts with x equal to 10, and we have that the graph is going to cross the x-axis. Okay, and so that will be the pattern of behavior we have. Again, I'm not drawing this according to scale, but this is just what we're going to have in the occurrence along the zeros on the x-axis. Okay, and now for which leads to the next portion. Okay, notice I started out below the x-axis and then had to cross above the x-axis. And one might ask, other than substituting, how would I know that I started below as opposed to above? And this is going to lead into, okay, what is going to be the end behavior of the graph of a polynomial function. And for what we have here, okay, so you have for the end behavior, of a polynomial function's graph. for what we have here, okay, let's say that for a polynomial function, okay, so you have f of x so you have a of n times x to the n you have plus a of n minus 1 times x to the n minus 1 you have going all the way down to a naught. A naught is going to be a constant, okay? And I'm just going to kind of give you a quick example. Yeah, like f of x is equal to 7x cubed minus 2x squared plus 3x plus 5. So this is like a specific case of what I have with the theoretical notation. Okay, now for this polynomial function, okay, you have, okay, notice for a of n, okay, for a of n x to the n, okay, this will be the highest degree term, okay, but it usually is, but it will not always be the first term that appears. There can be some exceptions. You'll usually see it at the front in most of the exercises, but there can be some counterexamples. And okay, so you have so a of n, okay, this will be the coefficient of the highest degree term and for the value n, n is going to be the highest degree, which is going to be the degree of the function. And with a of n, okay, a of n, you have the coefficient of the highest degree term in the polynomial. And again, the highest degree term is going to have, or will be, of degree n. And that, again, defines the degree of the function. Okay, so for a polynomial function of this type, okay, first of all, there are 4 possibilities that will arise. Okay, first of all, if we have, so I'm just going to do a little bit of a table layout. Okay, so you got your coefficient a of n, and we have the degree n, and we have the n behavior. Okay, so we have, first of all, okay, let's say that if a of n is a positive coefficient, and we have the degree n to be an odd value. Okay, so if I have a positive highest degree term and the degree is odd, now the n behavior, we say that we have down to the left and up to the right. But now let's say that if I have the leading term to be negative, and the degree, okay, is still odd. Okay, now you will have the end behavior to be the polar opposite of the first case. And in this case, we have up to the left and down to the right. And then switching over, okay, to the even powers. Okay, so if I have a positive leading coefficient, and this is going to be reminiscent of quadratic functions. In fact, quadratic functions will be applicable to the last two cases. Okay, like whenever we had the coefficient a to be positive, we had the graph opening up from the vertex. Okay, so if you have a positive leading term and the degree is even, we're going to have opening up both ways, up to the left and up to the right. And we have in the last scenario, okay, again, whenever you had the leading coefficient to not be positive but negative, while the degree of the function is even, you have moving the same way vertically at both ends where we have moving downward. So you have down to the left and down to the right. And let's say that if you're looking at determining the end behavior of the polynomial functions, okay, and we'll say that we have so we're looking at determining the end behavior of the following. Okay, and we'll say we have, first of all, we'll say that we have f of x is equal to 2x cubed plus 1. Okay, so you got f of x equal to 2x cubed plus 1. Okay, and just laying the groundwork, okay, for arriving at the end behavior. Okay, you can go ahead and identify the highest degree term or the higher degree term in this case. So that's going to be 2x cubed and looking at the end behavior, okay, again, we had a of n is the coefficient of the higher or highest degree term. N is going to be the higher or highest degree that appears in the function. So in this case, right, so you have the highest degree term or higher degree term, we have at 2x cubed. So we have that a of n is equal to 2. Okay, so we have a of n is positive. And from the x cubed, okay, we have that n is equal to 3. So in this case, okay, we have an odd value. So a of n is positive, n is going to be odd. So a of n is positive, n is odd. So the end behavior, you'll have down to the left and up to the right. And just kind of doing a quick sketch of what we have for this function f of x. Okay, so you have down to the left and up to the right. Okay, so this is the behavior of the graph of this particular polynomial function. So you got the end behavior down to the left and up to the right. Now let's say that if I have another polynomial function, and I'm also going to have this in expanded form. And so we'll say that we have f of x is equal to negative 5x to the fourth plus 2x plus 1 all right. And so for what we're going to have in this case, all right, so taking what we have now, so again we have another expanded form. And the highest degree term, okay, this is going to be negative 5x to the fourth. Okay. And with the highest degree term, so we have with the coefficients of the highest order term, okay, so a of n, that's going to be minus 5. So that is going to be negative, and for the degree of the highest order term, okay, that is going to be a 4. And 4 is an even value. Okay, so we've got a negative leading coefficient, and the degree, again, is even. So we have for the end behavior, so you got negative and even. End behavior, you have down to the left and down to the right. Again, just another rough sketch. Okay, and for this polynomial, once again we have the same vertical motion at both ends. Okay, so you have f of x, for f of x equal to negative 5x to the fourth. Plus 2x plus 1. Okay, and so just another scenario. And we'll say that we have f of x is going to be, let's say, 5 minus three x to the seventh. And so for the higher or highest degree term, okay, that's going to be minus 3x to the seventh. And for the leading coefficient, a of n, again we have minus 3. Okay, so the sign of a of n is negative. And for the degree n, okay, that is going to be at 7, which is odd. And this time around, okay, for what we have in the categories, okay, so whenever we have a of n to be negative while n is odd, okay, we'll have for the n behavior, okay, we'll have up to the left and down to the right. And again, just for the general behavior of the graph of this polynomial function, okay, so you have the n behavior, okay, so you have up to the left and down to the right. This is what we have for f of x is equal to 5 minus 3 times x to the seventh. All right. Now, in terms of tying in, okay, with what we have had with zeros and their multiplicities, okay, and tell you what, just for what we have among the components, okay, that will define the behavior of the graph of a polynomial function, okay, and let's say that, sort of tying in together, okay, let's say if we have if we were to determine, okay, first of all, the n behavior, so we'll do it this way. Let's say we have determined the zeros. And multiplicities. we have second of all, okay, so we have in the case of finding out, okay, what the value of the, again, along with the value of the multiplicities, okay, so if we're looking at where f of x is going to cross as well as touch the x-axis, and third, okay, again, we have the end behavior. Okay, and we'll say that we have so we have f of x is equal to, and we'll say we have negative 2x cubed times the square of x plus 4. Okay, so starting out with, okay, the factored form. Okay, so we have in the layout, okay, so looking for the zeros and their multiplicities, and also the locations where the graph might cross as well as touch the x-axis. Okay, so looking for the zeros and their multiplicities. Okay, so we have with the first variable factor, we have at x. So we can say we have x is equal to 0. And we have with the other variable factor, we have with the binomial x plus 4, for which we're going to have x equal to negative 4. And now for the multiplicities, okay, so we have 0 stems from the x factor, which is raised to the third. So 0 has a multiplicity of 3. And for negative 4, this stems from x plus 4, which is squared. So negative 4 is a 0 with a multiplicity value of 2. And in terms of what we have for crossing or touching the x-axis, again, for zeros of odd multiplicity value, okay, the graph is going to cross. So it's going to cross at x is equal to 0. And for even multiplicity valued zeros, okay, it'll be at those locations where, again, the graph is going to touch. And so we have to touch at x is equal to negative 4. All right, so we have these first two parts. Okay, now regarding the end behavior, Now, if we're looking for the end behavior, should be able to configure, okay, what the highest order term is going to be. Okay, so we have with the factors. Okay, what we're going to do here, okay, we have first of all, okay, we have at the front, we have negative 2x cubed, and so you're going to include not just the variable factor, but any coefficients that might be in the mix. So we've got negative 2x cubed at the front, and we have from the other factor, okay, for this particular binomial, I'm going to take the higher or the highest degree term inside the parentheses. So we have x from x plus 4, and that's going to be to the second. Okay. Okay, so we have with the highest degree term. Okay, so you got multiplying out. Okay, so you got negative 2x cubed and for the second component from x plus 4, x is the higher order. And again, that expression was squared, so the higher order portion we're going to have squared out. And for what we're going to have in the follow-through, so again we have negative 2x cubed, and for x to the second, okay, so that's going to be x squared. And I can now multiply together. Okay, so negative 2x cubed times x squared. Okay, so this will come out to minus 2x to the fifth. Okay, and so again, so just determine the highest degree term, and you don't even have to multiply like I just said, negative 2x cubed times x squared plus 8x plus 16, and the highest degree term would still be negative 2x to the fifth. So I was able to determine this relatively quickly, as opposed to having to do all the excess FOILing outs and all that stuff. Okay, so you got your highest degree term. So for the leading coefficient, or the coefficient of the highest order term, okay, so we have minus 2. Which had to be negative. And the value of n, okay, we had to be 5. Okay, and 5, okay, we had to be an odd amount. And for what we have regarding the end behavior, again, so whenever you have a of n to be negative and n is odd, you have the end behavior, you have up to the left and down to the right. All right. So just looking at tying the elements in together. Okay, so if I were to graph what I have with this particular polynomial function, okay, and so we have, and I'm going to utilize, okay, the zeros and the end behaviors if I were to graph. Okay, so we have for the zeros of interest, okay, so I have 0 and negative 4. And okay, now at the zeros, okay, so at -4, okay, the graph is going to touch the x-axis, and at x is equal to 0, okay, now the graph is going to cross the x-axis. Okay, now for what we have regarding the end behavior, okay, in terms of setting it up to get the end behavior and the touching and the crossing on the x-axis to intertwine. Okay, so end behavior, you have up to the left. Okay, so I'm going to have like an arrow or figure going up from the leftmost 0. And for down to the right, okay, we'll have that activity to start or to occur, okay, from the rightmost 0. So you have down to the right. And for what we have in between, okay, so I got up to the left, down to the right. So those are the end behaviors. And if I were to display what I have for f of x in continuous fashion, okay, so reading from left to right, okay, so you have the extreme end up to the left, okay, but if I go reading from left to right, so the graph is going down, and once I get to -4, the graph is going to touch, so it's not going to cross the x-axis, it's essentially going to bounce, and it's going to rise, okay, and then it's going to start to dip, and once I get to the origin, or x is equal to 0, okay, the graph is going to cross the x-axis, and the rest of the activity will be downward motion. Okay, so that will be the essentials of what we have for this particular polynomial function. And we'll start off with something in expanded form. Okay, so I'll just say that I have f of x is equal to, and we'll say we have 3x to the 5th plus 12x to the 4th minus 15x cubed. Okay, and now we have for this particular polynomial function, okay, if I were, okay, so this is an expanded form, and if I were to determine the zeros and their multiplicities, okay, so in this case, okay, and go from expanded to factored form, okay, so for 3x to the 5th, 12x to the 4th, and negative 15x cubed, okay, the greatest common factor, okay, we have 3 times x cubed. Okay, and factoring out 3x cubed, okay, so we have 3x cubed times what's going to be x squared plus 4x minus 5. And this trinomial I can factor. So for x squared plus 4x minus 5, okay, so this will factor to, let's see, have x plus 5 times x minus 1. Okay, so for the determination of the zeros and their multiplicities, again, just stressing the degree. Okay, so I have 3x cubed I have times the quantity, so I have x plus 5, and this will be to the first. And we have times the quantity of x minus 1, also to the first. And we have for the zeros. Okay, so we got with the variable factors, so I have x plus 5, and x minus 1. So we have with the first of these. Okay, so from x, okay, I have x is equal to 0. From x plus 5, I have x equal to negative 5. From x minus 1, I have x is equal to 1. And we have for the multiplicities, okay, so 0, okay, this would be a multiplicity value 3. Negative 5 has a multiplicity of 1, and we have x equals 1, okay, also with a multiplicity of 1, okay. And in terms of whether the graph crosses or touches the x-axis, if you notice, all of these multiplicities are odd, so you're going to have crossing exclusively. So crossing at x equal to 0, crossing at x equal to negative 5. Again, we have crossing at x is equal to 1. Okay. And in terms of what we have for the end behavior, so we have for the highest degree term, okay, so we have the expression is already in descending degree order. So that's going to be 3x to the 5th. Okay, and so for the coefficient, okay, a of n, okay, that is equal to 3. So that is positive. And for what we have in the case of the degree n, okay, that is 5, so you have an odd value. And again, we have the resurgence of the first of the 4 cases. And so we have for the end behavior, okay, have down to the left and up to the right. And just tying in what we have with the end behavior as well as the zeros. Okay, so we got our zeros. So we have negative 5, 0, and 1. And we have throughout. Okay, so we have the graph to be crossing for all of these zeros. Okay, and just taking what we have for the end behavior. Okay, so you have first of all, okay, for down to the left, I can just have the graph to be pointing downward from the leftmost 0. And for the extreme end, we have up to the right, and I can do this with the figure pointing upward, up and away to the right, okay, from the rightmost 0. In other words, away from x is equal to 1. And then for everything else in between, okay, so we got, so if I read from left to right, just to fill in the spaces, okay, between the zeros. Okay, so have reading from left to right, so starting out again beneath the x-axis, once again x equals negative 5, okay, the graph is, we have to cross, then it's going to descend, and you have cross at x is equal to 0. So it's going to dip, and then it's going to rise up again, and so you're going to have x at x equal to 1. Okay, the graph is going to cross once more, and we have for this function is going to stay above the x-axis as we get to those values greater than 1 for x. So this is the dynamic set of dynamics that will play out for what we have for this particular fifth order polynomial function. All right, and in terms of what we have with end behavior, zeros, and multiplicities. Let's see what we get for the zeros, multiplicities, where the graph crosses or touches the x-axis, as well as the end behavior. And we'll say in this one, we'll say we have f of x is equal to, we'll say we have negative 2x to the fourth. Minus 16x cubed and we'll say in this one, I'll change that to subtraction as well. Okay, so let's see what we get. Okay, in the case of f of x is equal to negative 2x to the fourth minus 16x cubed minus 32x squared. Okay, for this fourth order polynomial expression, okay, okay, we look for the zeros. Okay, so here we have the expanded form, whereupon we have f of x is equal to negative 2x to the fourth minus 16x cubed minus 32x squared. Okay, and if we look at factoring, okay, now this example, okay, a little bit different, okay, in terms of factoring, okay, because we're normally in the mode, especially when there's a common factor, to go ahead and pull out, okay, the greatest common factor. But since we have negative terms throughout, okay, and we have not exactly the greatest common factor, but it's additive inverse. Now, the greatest common factor would be 2x squared, but since I have an excess of negatives, I'm going to factor out not 2x squared, but its additive inverse. We're going to have negative 2x squared to be factored out. And if I do that, okay, so you got negative 2x squared into negative 2x to the fourth. So that's going to be x squared, negative 2x squared into minus 16x cubed. That's going to be a positive 8x. And negative 2x squared into negative 32x squared. Okay, so this will be a positive 16. And going from the expanded form to arriving at the completion of the factored form. Okay, so I got negative 2x squared. And for the trinomial, we have an x squared plus 8x plus 16. And if I factor, I'm going to have the same binomial with x plus 4. And then finalizing, okay, the factored form. Okay, so you have f of x is equal to negative 2x squared times, okay, what is going to be x plus 4 raised to the second. And again, just stressing the degrees so as to identify the multiplicities along with the zeros. So again, we have negative 2x squared again, we have times the quantity of x plus 4 also squared. Okay. All right. So looking at identifying the zeros. Okay. So you have with the x factor, we have x equal to 0, and with the x plus 4 factor, okay, I have x equal to negative 4. And for the multiplicities, well, both degrees we have at 2, so 0 is going to have a multiplicity of 2. Negative 4 likewise. And in terms of whether the graph is going to cross or touch the x-axis, okay, so both multiplicities are even. So that means that you'll have, with respect to the x-axis, okay, the function is going to touch at x equal to 0 as well as x is equal to negative 4. And for what we have concerning the end behavior, okay, for the highest degree term, okay, that's going to be negative 2x to the fourth. And so we have for the highest degree term coefficient, a of n, okay, that is minus 2. So that is negative. And again, highest degree term defines the degree of the function, and that degree is 4. So that is an even value. So for a negative highest order term coefficient, and where the degree is even, you're going to have for the end behavior, okay, you'll have the same motion vertically, where at both ends the graph will be moving downward. So we have for the end behavior, okay, this is going to be down to the left as well as down to the right. And just looking at how it all comes together. Okay, so we have with our two distinct zeros. Okay, so we have x equal to 0. And x equal to -4. You can have both of these zeros. Okay, the graph is going to touch. And for the end behavior, okay, so you have down to the left and down to the right. So down to the left, okay, we have proceeding downward to the left of x equal to -4, and down to the right we have proceeding downward as we go past x equal to 0. And then for what we have in between, so if I read this graph in order from left to right, I'm just going to restate. So you have down to the left, or in Alex's terms, we have falls to the left and down to the right. This terminology would be falls to the right. Okay, and then just filling in the empty space. Okay, so if I proceed from left to right, okay, so you have starting out underneath the x-axis, and once I get to x is equal to -4, again the graph is going to touch. So it's essentially going to bounce off the x-axis, then it's going to rise again, and once we approach x equal to 0, it is going to touch but not cross, and never is the graph of this function going to be above the x-axis. It'll be on the x-axis but never cross to where it is above. Okay, and so this would be the essence of what we have for this particular polynomial function. Okay, so we have for f of x equal to -2x to the 4th minus 16x cubed minus 32x squared. All right, and there'll be some other characteristics. Okay, we'll be running across, okay, with polynomial functions, and then we're going to cross over to what will be regarded as operations between rational functions.